This material and energy balances video is titled Relationships Between P star, the vapor pressure, and T, or T boiling. And it will help you to obtain the conditions at which vapor-liquid equilibrium is applying. So for any given P star, any given vapor pressure, the corresponding temperature at which that substance boils is called the boiling point. And for every temperature, there is a corresponding vapor pressure at which the substance will also boil. And what I told you in the last video still applies. If a phase diagram exists, or if you have access to that phase diagram, you'll definitely want to use that because that is always the most accurate in terms of somebody actually studying it and telling you what the phase behavior is. But if not, you can use one of the following methods. I'm going to start off with one of these methods out of the following ones that I'll talk about in this video is actually the least useful, but it's important for deriving another more useful equation. This is called the Clausius equation. And you will go into more detail about how this equation was derived in a future class. For material and energy balances, I'm not necessarily so much interested in where this comes from, but what we can derive from it. The Clausius equation says that the partial derivative of the vapor pressure, dP star, with respect to dt is equal to delta HV over T times the difference in the specific volume of the gas minus the specific volume of the liquid. Now, there are a few unfamiliar terms in this equation, so I'm going to break this down. Once again, you may in a future class learn where this is coming from, but for now, we're just going to use it as a relationship between P star and T. I like to think of dP star dt as the slope of the vapor-liquid equilibrium line on the phase diagram. Slope of the vapor-liquid equilibrium line from the phase diagram. Delta H hat V is the specific enthalpy of vaporization. And this is the energy that it takes to vaporize 1 kilogram of the substance. Actually, wait, I made a slight mistake. So I wrote hats here, and I said that I was going to try and fix this notation. I'm not sure why this book doesn't use the notation that all others do. I'm going to use underbars here. And underbar are going to be molar enthalpies. Right, so specific has to do with per mass, molar has to do per mole. Molar enthalpy of vaporization. And this is the amount of energy it takes to vaporize 1 mole of a substance from the liquid phase to the vapor phase. Amount of energy required to vaporize 1 mole of the substance. Okay, these V underbar G and V underbar L are the molar volumes. Molar volumes. So you can think of this as the reciprocal of the density, but the difference is the density is per kilogram, not per mole. So molar volumes is the volume occupied by 1 mole. By 1 mole of a substance. And T, of course, is just temperature. Now, I mentioned that of the methods that I'll talk about today, the Clausius equation is the least useful, and that's practically because it doesn't tell you what P star or T is directly, right? It's a differential equation. It's the change in vapor pressure with respect to the change in temperature. So without being able to integrate this, it really does you no good. The reason why I introduce it then is because integration of this Clausius equation actually does give us a useful expression for P star as a function of T. And this was derived by Clapeyron, or he modified the Clausius equation. And this is called the Clausius-Clapeyron equation. And I mix this up every single semester. I give Clausius more credit than he's due. Clapeyron is he was actually the person who made this equation. And then Clausius came along and made some simplifications and integrated it. So that was the Clausius equation before, not the, it was the Clapeyron equation before. I keep messing this up. Clapeyron equation is the non-useful one. The Clausius-Clapeyron equation is slightly more useful. So it's the Clausius-Clapeyron starts with the Clapeyron equation, and it makes the following simplifications. The first simplification is that the specific molar volume of the gas is much greater than that of the liquid. And if you think about it, this assumption really makes a lot of sense because a gas will always take up more volume than the corresponding liquid would. So if you assume that the volume of the gas is much greater than the volume of the liquid, then in your Clausius-Clapeyron equation, which is again dP star with respect to dt is equal to delta HV over T times Vg minus VL. You can simply cancel VL. You can assume that Vg minus VL, if Vg is much, much greater, is just going to simply cancel what the VL is. And then from there, you can assume ideal gas. So you have to know at which conditions the Clausius-Clapeyron equation applies, and it only is useful if these conditions are met. But if you assume ideal gas, then the molar volume of the gas, remember this is volume per mole, is equal to, let's see, PV equals nRT, right? So it's RT divided by P. And then the last assumption that you have to make is that assuming that the enthalpy of vaporization is not a function of temperature or pressure, assuming that delta HV is not a function of temperature. And this one is a little bit of a weak assumption. So HV is a function of temperature, but unless you know what that dependence is, you can't do the next step, which is integration. All right, so if I'm going to assume that, then I'm going to get it into a separable differential equation form. So dP star dt is equal to delta H underbar V over RT squared over P. And now I have a separable differential equation. So separable differential equations require that I get everything on all the variables grouped according to the side of the equation. I guess technically this should be a P star, right? Because we're talking about phase equilibrium. So I'm going to bring that P star over to the other side. And I'm also going to bring the dt over to the other side such that I can integrate the expression. So dP star over P is equal to minus delta HV over R, 1 over T squared dt. And when I integrate this expression now, I can take the delta HV over R out of the integral because they're both constants, at least with respect to temperature, or at least that is what I'm assuming. So the integral of dP star is ln of P. So ln of P star is equal to delta HV over R, and the integral of 1 over T squared is minus 1 over T. And this is the final derivation of the Clausius-Clapeyron equation. Or is it? Actually, I've forgotten a major part here. Forgotten that because I have an indefinite integral, I'm going to have a constant of integration here. So plus B is what your book calls it, but it usually is a C from what I learned from calculus. C is the constant of integration. So this is the constant of integration. So this form of the relationship between P star and T is a lot more useful because it's a direct algebraic equation. In other words, if I tell you what the temperature is and I tell you what the substance is, you could look up what the molar enthalpy of vaporization is. I forgot to make it molar enthalpy of vaporization. But the last part, what you need to know is you need to know what this B is. You need to know the constant of integration. So therefore, you need to know what, you have to have one data point. So if I tell you that the boiling point of water at 1 atmosphere is 100 degrees Celsius, right? I can plug those numbers in to the Clausius-Clapeyron equation. I can calculate or compute what that value of B is that I can then use to find what the boiling point of water is at other pressures. So Clausius-Clapeyron is useful, but it requires you to have at least one known data point. And it also assumes that these preceding three assumptions are valid. Because these assumptions oftentimes are not very valid, and also because sometimes we won't have a data point to use, we can use a third relationship between P star and T. And that third relationship is Antoine's equation. The Antoine equation is purely empirical. And if you're not sure what that word means, empirical means observed directly by experiment. So that means there's no theoretical basis for the Antoine's equation. No theoretical basis. And just as an aside, empirical is a word that you will undoubtedly hear many times in the rest of your chemical engineering education. This means observed directly from experiment. And there are various forms of the Antoine's equation with different units, but the one that you will see in this textbook goes like this. It says that the log base 10 of P star is equal to A minus B over T plus C. Now in this equation, this is it, by the way, this is the Antoine's equation. A, B, and C are parameters. So these are the fit parameters from experiment. A, B, and C are parameters that are specific to each species. To each species. And once again, they are derived from experiment. T is the temperature. And remember, in a previous video, I said 99% of the time in engineering, you will use the absolute temperature. This is the other 1%. So this is temperature, and this is oftentimes in degrees Celsius. But you have to use the units that your resource gives you. So in a moment, I'll show you where to find the values of the Antoine's constants, A, B, and C. You need to use whatever units that your table tells you. So in the back of the book, this is in table B4, by the way. So find these in table B4. B4, it has in the footnotes that you want to use temperature in degrees Celsius, and P star for this particular A, B, and C is in millimeters of mercury. So they're odd units, definitely. But again, if you have a table that says to use different units, you want to use that. That's really all to say about the Antoine's equation. In the coming class periods, we'll get some practice using the Antoine's equation. I'll share that in this class, most of the time when we're looking up or using a functionality or want to know what the P star is for a certain temperature, we're going to use the Antoine's equation. So we'll definitely get comfortable using this one in practice. That's going to wrap up this video.